Hey there, AP Pre-Calc. Let's talk about logarithmic functions today in lesson 2.11. I'm Miss Adams from Flamingo Math. So today's goal is to summarize all the key characteristics from log functions before we start talking about the properties of logs and solving both logarithmic and exponential equations, and then moving into modeling with real-world applications. We've talked about the domain of a logarithmic function from the last lesson, and you can read that here in this text box. And we also have looked at the properties of the graph of logarithmic functions. Some of the key points are the x-intercept at 1, 0, the fact that there's no y-intercept. We know the y-axis is the vertical asymptote for the graph. We know that if the base is bigger than 1, we have an increasing function. If the base is a fraction between 0 and 1, we have a decreasing function. And we know that the key points contain 1, 0, the base, and 1 over base, -1. And finally, we know that the graph is smooth and continuous, and it has no sharp corners or gaps. So let's jump right into the lesson. We want to find the domain for each of these logarithmic functions. For part A, log base 2 of x plus 5, we're going to consider the argument x plus 5, and we want to know when x plus 5 is greater than 0. So that would happen when x is greater than -5, which leads us to the conclusion that the domain has to go from -5 to infinity. For part B, we have log base 3 of the quantity 1 minus x divided by 1 plus x. So in a similar fashion, we know that 1 minus x over 1 plus x has to be greater than 0. In this example, I'd like to use a line test to determine where my statements are true. So in this case, we have two critical numbers at +1 and -1. So if we think about the number line, the all real number line, and we are going to test, this is our test values here. And let's say, for example, I test the number -2. In the expression, 1 minus -2 and 1 plus -2 gives me a negative value. So we have a false statement in this section of the real numbers. Let's try testing 0 in the middle section. If you substitute 0 into our argument, 1 minus 0 and 1 plus 0 gives us 1 over 1, which is a positive interval. So everything in this interval is greater than 0, which makes our condition hold true. This section is true. And then finally, in the last section, if we test +2, we're going to end up with 1 minus 2 and 1 plus 2, which is a negative area. So this interval is false. And we want the inequality to be greater than, so we want open circles. That gives us the domain as -1 is less than x is less than 1. Now you could also do that algebraically, but that's a little more tedious, and the number test strip works really well in this case. In part C, we've got log base 1/2 of the absolute value of x minus 2. So absolute value has two solutions because the x minus 2 can be greater than 0, or inside that argument, we want the opposite of x minus 2 to be greater than 0. Solving the first inequality, x is greater than 2, or this is an or statement based on the rules from absolute value, or the opposite of x plus 2 is greater than 0, when the opposite of x is greater than -2, and then dividing by a negative on an inequality flips the inequality sign, and then out pops our domain statement for part C. So the domain will go from -infinity to 2, and then skip over 2 and run from 2 to infinity. So there's some examples of domain for logarithmic functions. Moving on to example 2, we've got the graph of a log function that's shown, and then our graphs are labeled A, B, C, D. So this one is a decay, this one is a decay, this is a growth, this is a growth. Log base 2 of x is going to be a growth function, and this growth function looks like graph C to me. So f of x is graph C. This is f of x log base 2 of x. On the second graph, g of x, log base 2 of negative x, the negative would cause the graph to reflect over y. So this negative is causing reflection over y, this negative here. That's going to make our graph a decay graph. And we also know, since it's reflecting over y, our graph itself will be on the left side of the vertical asymptote. So looking at the graphs, can you determine left side of the vertical asymptote is going to either be A or D. Now compare, graph A is a decay graph, but graph D is a growth graph. So g of x goes with graph A. G of x belongs to graph A. This is g of x log base 2 of negative x. Graph C is got a negative in front of the logarithm, so that negative is going to reflect our graph over the x-axis, this negative here. And that's going to make the graph become a decay function. And the only other decay function left in our choices is graph B. So B is h of x, negative log base 2 of x. And then by default, graph D belongs to k of x. And if we analyze y, we have the negative on the argument that causes a reflection over the y-axis, and the base being a half, that's a reflection over the x-axis. So it's going to reflect once to make it decay and reflect again to make it a growth. So we're back to being a growth function, and the only growth function left is graph D. And it would also be on the left side of the vertical asymptote based on this negative here. And then a little bit of critical thinking based on your findings. Which graph above would also be correct for log base 1/2 of x? And in my thinking, since log base 1/2 of x could be written as negative log base 2 of x, then we have a reflection across the x-axis. So only graph B would match that challenge to us. You could use your graphing calculator and verify that these two are the same. Moving on to example 3, we want to sketch the graph of the parent function log base 2 of x and substituting our x values into the function, we get 0, 1, 2, and 3. So we can graph those ordered pairs. 1, 0, 2, 1, 4, 2, and 8, 3 gives us the graph of f of x. How's the graph of g of x, negative log base 2 of x, translated from f of x? Well, in our last example, we learned that this negative in front causes f of x to reflect across the x-axis. And if we wanted to write a rule for g of x, the rule for xy from g of f of x to g of x would be keep the x and do the opposite on y. That's going to make our table look a little bit different. So the g of x table, using the same x values, 1, 2, 4, and 8, we want the opposite of 0, that's still 0, the opposite of 1, the opposite of 2, and the opposite of 3. And that's going to cause our graph to go as a decreasing graph, g of x in green. If we analyze both of those graphs for f of x, the domain is 0 to infinity. The range is all reals. We've got an increasing function because the rate of change is positive. Our graph is concave down. And the reason our graph is concave down is because the rate of change is decreasing. We have 1, 0 for our x-intercept, and the vertical asymptote is x equals 0. That's the f of x analyzing. And analyzing g of x, the domain stays the same, 0 to infinity. The range is all reals. We've got a decreasing function because the rate of change is negative. We have a concave up graph on the green graph. And the reason it's concave up is because the rate of change is increasing. We still have 1, 0 for our x-intercept, and we still have the same vertical asymptote at x equals 0. So as we go through the unit, you get better and better at analyzing these graphs. For example 4, we're given the function and we want to determine the asymptotes and the end behaviors using limit notation. So I like to see, first of all, looking at the argument, we've got x equals 1 is our vertical asymptote. And I'm thinking about this is going to be on the right side of the vertical asymptote. So it's going to be an increasing function. And that helps me to write the limit notation. So the limit as x approaches 1 from the right on that function y is going to go to negative infinity. So I'm thinking about the graph this way. We're going to scoot over to 1. That's our vertical asymptote. We've got this kind of a graph, right? So as we go to 1 from the right, our graph is bounded down. And then the limit as x approaches infinity on y goes to positive infinity. So that helps us to get a handle if you want to make a little sketch on your paper to understand the behavior of the graph. For log base 10 of 2 minus x, think about that as the argument. We can rewrite that argument, y equals log of negative x minus 2. Think about it that way. So that's going to cause the graph to flip. It's going to be left of the vertical asymptote. So this will make the graph be left of the vertical asymptote. It's going to be a decreasing graph. because of this negative here. We know that x equals 2 is the vertical asymptote. Let's see, we need to label that one. And what do we know? We've got the limit as x approaches negative infinity on the graph of y is going to be unbounded upward, and then the limit as x approaches 2 from the left on the graph of y will be unbounded downward. And just so you get an idea of what my brain's thinking, the graph would look like that to me. Moving on to C, we've got two things going on. We've got a negative here in the front. This -1 is going to make our graph be a decreasing graph, but we're translated 4 units left and 2 units up for that x-intercept value. So we got a graph that is on the right side of the vertical asymptote, but it's a decreasing graph. Can you get that in your head with the way the graph looks? We've got -4 is our vertical asymptote. We've flipped over and we've got a decreasing graph. So x equals -4 is the vertical asymptote. The limit as x approaches -4 from the right of our function is unbounded upward, and the limit as x approaches infinity on our graph is heading to negative infinity. The sketch always seems to help me out. And finally on D, we've got the log of x minus 3. So what's happening there? We're staying on the right side of the vertical asymptote. It's just a normal increasing log graph. X equals 0 is our vertical asymptote, and the limit as x approaches 0 from the right on the function is heading to negative infinity, while the limit on the right of the graph is unbounded up. Not so bad. Let's move on to example 5. We've got a table of values, and we're going to determine whether the function is increasing or decreasing, and we want to talk about the concavity of the function and make a sketch about the function and determine the domain if that's possible. So looking at the y values, it appears to me that f of x is increasing. It's an increasing function. That means the rate of change is positive. It's going to be concave down. That's telling us the rate of change is decreasing. And our graph would have a vertical asymptote at maybe 1. We've got a table, so 2, 0, 6, 1, 26, 2. So way out there, we've got this kind of a graph. This is x equals 1. That gives us a domain of 1 to infinity. So that's not so bad. How about B, g of x? What's happening here? We've got decreasing values, so g of x looks like a decreasing function. G of x is decreasing. That means our rate of change is negative. So our graph is going to be concave up, which means the rate of change is increasing. we've got a vertical asymptote at -2. I'm getting that from these values here. And -1, 0, 1, -1, 7, -2. So we've got this decreasing graph here. And x equals -2 is our vertical asymptote. So that gives us a domain from -2 to infinity. And then we've got an application problem. I believe this is our last example here. You need your calculator handy. I've already pre-worked these on my calculator, so I'm not going to pull that screen up, but I've got this function where t is this. We're asked to calculate t, so for each k value here, I'm going to divide by 0.0625 and find those values. We've got 0, 11, 0, 11.090, 22.181, 28.668, 33.271, and 36.841. How long does it take before your investment doubles? It looks like in the second column, right here, about 11.09 years. So we want to write a sentence about that. About 11.09 years before the investment will double. Use a graphing calculator to graph that graph on the grid provided. So we've got 1, 0 here. At 2, we've got 11. At 4, we've got 22. At 6, 28. At 8, 33, and at 10, 36. So we've got this type of a graph here. In part C, the last example, suppose you had $1,000 to invest. Your function for the amount in the account at any time t would be given as a of t. Use this function to verify your answer in part A. So what part A gave us was 11.090. If you evaluate inside the function e to the 0.0625 times 11.09 for the t amount, our final amount in the account after about 11 years is $19.99.96. This is the end of our lesson on logarithmic functions.